Hello everybody. We now turn our attention to Chapter 6 and the discussion of atmospheric waves. We'll start off by laying some of the groundwork necessary in order to understand these waves using mathematical notation, and then we'll eventually dive into a discussion of different types of waves that appear in the atmosphere and how energy is being transported by these waves. So waves are key to atmospheric behavior because they have basically two important consequences. First of all, waves are responsible for the transport of energy in the atmosphere, moving it from one location to another, and it's also responsible for mixing the air, that is, the generation of turbulence generally associated with wave breaking. These type of waves appear in generally any fluid context, whether in the ocean or in the atmosphere. However, the waves in these two mediums tend to be very different from one another due to compressibility of the atmosphere and incompressibility of the ocean. So for meteorological purposes, there are a number of different waves that we're interested in, ranging from the largest planetary scales down to microscale, where we have sound waves, for instance. So on the planetary scale, we have Rossby waves, which propagate around the entire planet, usually with wave numbers of 5 or 6. We have internal gravity or buoyancy waves, which are responsible for the transport of energy within a fluid. We have inertial waves, which are associated with Coriolis motions, inertial gravity waves, such as surface waves in the ocean, topographic waves, which are associated with mountain response or Lee response to imposed wind field, and we have shallow water gravity waves occurring along the ocean surface, such as one would see for tsunamis, for instance. Sound waves, as I mentioned earlier, occur on very, very fine scales, and so typically are not of interest for meteorologists, who are interested in more large-scale weather phenomena. Further, sound waves tend to be very weak energetically, and so do not carry much energy along with them. For large-scale mid-latitudinal waves, Rossby waves in particular, these are critical for weather forecasting and transport, as we saw in our discussion of quasi-geostrophic theory. For large-scale waves in the tropics, such as Kelvin waves, mixed Rossby gravity waves, these type of waves are very important as well, but of a very different character. In particular, in the mid-latitudes, we have Coriolis forcing and a strong beta effect in that region, whereas in the equatorial regions, we only have the beta effect and no background Coriolis forcing. Consequently, we will see that we observed much significantly different wave-like behavior in this regime. Waves can also be unstable. You can think, for instance, of the baroclinic instability that we talked about in quasi-geostrophic theory. As that grew, it eventually became unstable, leading to an overturning of the wave and mixing across scales. So we saw large-scale wave behavior, that is, planetary-scale waves, collapse into small-scale wave behavior. And this emphasizes the non-linearity of the equations of motion as we see this interaction across atmospheric scales. Here is a simple example of atmospheric waves taken recently in California. Here we see basically wave-like activity in the clouds. And this type of activity is basically associated with natural buoyant oscillations within the atmosphere that are leading to regions at the crest of these waves achieving saturation and hence condensation, leading to the generation of clouds, whereas regions in the trough are unable to obtain saturation, and so you generally get clear skies within that region. This type of behavior is clearly exhibited all across the world and is a very common example of atmospheric wave motion that we can see. Alright, so let's talk about waves in general. Waves generally are sinusoidal, that is, having both crests and troughs. We're going to define a wavelength, Lx, along the wave, which is going to be the distance between subsequent troughs, or analogously distance between subsequent crests. This then motivates a concept known as the wave number, which is 2 pi over Lx in the zonal direction, denoted by character k, and this has units of 1 over length. Since this is the inverse of the wavelength, we actually have that very long waves have very small wave numbers, down to k equals 0, which represents essentially constant background, whereas large wave numbers correspond to very short waves. In 2D, we have to deal with a slightly different scenario. We have three types of wavelengths that we now need to consider. We need to consider a wavelength along the propagation of the wave, here denoted by L. As well, we need to consider wavelengths in both the x and y direction. Using the definition that wavelength is the distance between subsequent crests or troughs, we can then depict the length, the corresponding wavelengths in each of these three directions on this diagram. In particular, recall that in a Pythagorean relationship, you generally have that the hypotenuse is equal to the sum of squares of each of the corresponding sides. However, here we actually have an inverse relationship, and so the hypotenuse is shorter than either of the two corresponding wavelengths along each coordinate direction. That is, L is less than both Lx and Ly. Due to the fact that the Cartesian or Pythagorean relationship actually holds in wave number space rather than holding in wavelength space. That is, we can define a wave number along the flow by kappa, which is equal to the square root of k squared plus L squared. You'll then observe that kappa must be larger than both k and L respectively, and so the wavelength L must be smaller than either Lx or Ly. We also denote a wave number vector here, shown by boldface kappa, which is actually equal to the wave numbers k and L in each of the coordinate directions I and j. So in 2D, we have wavelengths Lx and Ly. From geometric considerations, we can actually show that 1 over L squared is actually going to be given by 1 over Lx squared plus 1 over Ly squared, which then applying our definitions of wave number is equal to k squared plus L squared over 4 pi squared. So recall these definitions, and as they will be used throughout our discussion of wave theory. We have a wave number vector, we have constant phase lines, that is, we have an equation which represents lines of constant phase, which is defined by k dot r or kx plus ly. That is, whenever this equation has a single value, then you will be in the same phase position along the wave. So for instance, the zero value may correspond to wave troughs, in which case whenever you have a zero value for constant phase lines, you will then be at a trough region of the wave. So for 2D traveling waves, we also have to introduce a concept known as frequency. Here we've denoted with nu. Nu is defined as 2 pi over t, where t is the wave period. Now consider a wave which moves from an initial location, shown here at the bottom at time t1, to a final position up to the northeast at time t2. This wave will pass through a distance delta s along the wave, as well as distances delta x and delta y in each coordinate direction. Using the same inverse geometric relationship that we saw for wavelengths, we can write that 1 over delta s squared is equal to 1 over delta x squared plus 1 over delta y squared. Here, delta s is also defined as the distance covered by the wave over a period delta t, and for a wave oscillating with frequency nu and wave number kappa, this distance is actually equal to nu over kappa times delta t. In each coordinate direction, we also have analogous distances covered, which are given by nu times delta t over k and nu times delta t over L, which represent the speed of the wave in each coordinate dimension. This concept is known as the phase speed. That is, it is the speed at which crests and troughs of the waves propagate through space. And it is defined as delta s over delta t, or nu over kappa. In each coordinate direction, we also have phase speeds in x and y, which are given by nu over k and nu over L. So for phase speeds in each direction, the formulas are shown here. This is the speed, again, that the crest or trough of the wave propagates. Note that one can visualize this as well as an observer standing on a shoreline. If the shoreline is aligned with the x-axis of the flow, then one will observe that there is a different rate at which crests and troughs are propagating along the wave than they are along the shoreline. In fact, if one goes to the infinite case, that is where waves are propagating perpendicular to the shoreline, one will actually then obtain an effectively infinite distance between troughs, between adjacent troughs, and so leading to what is observed to be an infinite phase speed along the shoreline. In the case where waves are propagating parallel to the shoreline, in that case, then the distance between wave troughs will be exactly the same as the regular distance between troughs, and so you'll then obtain that the phase speed along the shoreline matches the phase speed of the wave itself. Okay, so this motivates a concept known as the dispersion relationship. So dispersion relationship basically says that the phase speed which is defined by frequency divided by wave number, can vary depending on the wave number itself if this relationship has different values for different wave numbers. So that implies that for certain physical relationships or certain wave types, you'll actually have different wavelengths which are propagating at different speeds. So a composite signal, that is a signal composed of a sum of different waves, will break up in accordance with the dispersion relationship, and you'll tend to get either faster propagation of short waves or slower propagation of short waves depending on the physical relationship. This leads to a distortion of the signal over time. Non-dispersive waves, which include shallow water gravity waves or waves which propagate along the ocean surface, have a single phase speed associated with all wavelengths, and consequently any initial signal, so any initial composite signal, will always propagate as a single packet and consequently will not deform over time. So the dispersion relationship then is defined as the function frequency in terms of corresponding wave numbers. So we're going to discuss now what happens when you compose multiple wave numbers. The composition of two wave numbers tends to create both constructive and destructive interference of the wave pattern. So in fact, adding together two waves of approximately equal wave number will produce a wave envelope similar to the one which is depicted here. Now, individual waves, a single wave number, for instance, will only oscillate up and down, and there is no mechanism by which energy can be transported with the flow. However, the presence of a wave packet allows for propagation of energy along with the wave itself. So energy distribution then is the property of a set of waves rather than a single wave. And as we will see, it propagates in alignment with the propagation speed of the wave packet itself. Note that the wave packet speed does not need to match the phase speed of the waves. In fact, it in general will not, because the wave packet is composed of waves of different frequency. So a wave pattern, which consists of a succession of wave packets, is then considered. Within each packet, the wave will propagate with a phase speed c, which is given by nu over k. However, the propagation speed of the wave envelope actually propagates at what is known as the group velocity. In 1D, it turns out that this quantity is actually given by the derivative of the frequency with respect to the wave number k. In higher dimensions, this is actually given by the gradient of the wave number of the frequency with respect to wave number space. So the individual components of the group velocity are then di nu di k and di nu di L in 2D. So keep this in mind, that the phase speed of the wave and the group speed do not necessarily have to agree with one another. In fact, we can visualize that here using these two short animations. Here showing propagation of phase given by the blue crests and troughs, and corresponding propagation of wave packets. Wave packets are delineated by the green dots, and the red dot shows propagation of a single crest of the wave. As we can see, the red dot is propagating at approximately twice the rate of the wave packet itself. Note that one can even have that the phase and group speeds are in the opposite direction of one another. So here we see a wave packet which is propagating to the right, whereas the phase associated with these individual waves is propagating to the left. So watch this closely for a moment and you'll clearly see the differences between the phase and group speeds. Okay, so in order to actually look at wave behavior in the atmosphere, we're going to rely on a concept known as linear perturbation theory. What that does is basically assume that every variable that we're interested in, that is our typical set of atmospheric variables, including 3 velocity components plus 2 thermodynamic components, is equal to a mean value, which is here denoted by an overbar, and a perturbation here denoted by a prime. So this approach can be done in general for any equation set effectively. Substituting this in does not lead to any approximations. Approximations will follow later in the theory. So we now impose our assumptions and constraints on the problem. Typically, we need to come up with a mean state such that perturbations from the mean state are in general small. If we can construct the mean state in this manner, then the product of perturbations will be very small, and then one can typically drop the product of perturbations from the resultant equations. So to see an example of this in practice, consider for instance the nonlinear advection of zonal velocity, here given by u times du dx. If we expand each u in terms of the mean and perturbed state, we then expand it out to obtain 4 terms associated with this expression. Now the first 2 terms are assumed to be 0 because the mean state as we've constructed it has no zonal dependence. That is, it is assumed to be an average in the zonal direction, and hence the derivative of x of u bar is exactly equal to 0. Further, the last term, which looks like u prime times du prime dx, this term is dropped as a nonlinear term because it is the product of 2 small perturbations. Consequently, the nonlinear u du dx term is approximated by a linear term which looks like u bar times du prime dx, where the active dependent variable is u prime here, and u bar is simply a function of space. So for linearization, this process can be repeated for each of the equations of motion. So here, for instance, we can use the u momentum equation, here assumed constant density with 0 friction. We apply the expansion that we saw on the previous slide to the material derivative term and apply the fact that we can also expand the pressure in terms of a linear expansion. Since p bar is again has 0 zonal component associated with it, this then reduces to di p prime dx, and so we obtain a linearized equation as shown below. So our objective then will be to take these linearized equations of motion and look for 1D wave solutions. From mathematics, actually, it can be shown that any linearized set of equations will generally have solutions which are wave-like. That is, solutions which look like either complex exponentials or trigonometric quantities. One simple wave-like solution that we can look for is that the perturbation is equal to a reference magnitude u0 times the cosine of kx minus nu t. If one factors out the k from this expression, this will then become cosine of k x minus ct. Now x minus ct is an interesting expression because at time 0, this will actually have the form of cos kx. However, it will then lead to the generation of characteristics which propagate at speed c. That is, we will see that the wave propagates forward as a function of time with a speed given by nu over k, or the phase speed associated with the wave, which is exactly expected from our construction of phase speed earlier. So here, recall that the wave number k is 2 pi over Lx, and the frequency is 2 pi over the period. So The unfortunate thing about using a cosine rather than a complex exponential is that this form of the wave actually fixes the phase over the wave. That is, you'll notice that at time x equals 0, or at time t equals 0 and position x equals 0, all solutions must have u prime equal to u naught. However, there are many possible solutions with wave number k, which can be shifted either to the left or to the right. So in general, we will use complex numbers and use a complex expansion, which looks like u prime as shown below. Here it's the real part of u naught times e to the ikx minus I nu t. This again has a phase speed associated with it given by nu over k, and u naught can also be a complex number having both real and imaginary components associated with it. In 2D, this expansion simply adds another wave number to the contents of the complex exponential. So here we have u prime being equal to the real part of u naught e to the ikx plus ily minus I nu t. So recall that this complex exponential can be expanded using Euler's formula in terms of cosines and sines, and hence we recover why this complex exponential form is able to account for all possible phases of the underlying wave. That is, it includes both a magnitude and a phase shift, which is obtained from the sum of trigonometric functions. Note that generally in this form we'll both have real and imaginary components which arise from this analysis, but only the real part has physical meaning. In 3D, we again add another wave number to the expansion, here obtaining u prime equal to the real part of u naught e to the ikx plus ily plus imz minus nu t. This wave propagates in all three dimensions. So we can also have an additional form where we no longer assume wave-like solutions in one particular dimension because we may introduce nonlinearity, for instance, in the vertical direction. In that case, we can have u naught as a function of z, and we can have a wave propagation in the 2D horizontal plane, as shown below. So these are all the possibilities that we'll look at for wave expansions. Just make sure that you understand these as we move forward, as they'll play an important role in understanding the different waves that occur in the atmosphere.